And now we will talk about a C code that perform the sort of an array. And we will have this example to put everything that we study together. So this C sort example illustrates the use of assembly instructions for a C bubble sort function. There are many types of the sort function. One of the famous types is the bubble sort. So the sort make use of a function called the swap. This swap function or swap procedure is a leaf procedure. And as you can see here, the job of the swap procedure, if you have two variables, vk and vk plus 1, you want to swap the values of those two variables. So what you do, you define a temporary value, and first you get the value of the vk and assign it to the temporary variable, and then now since you save it, you can overwrite the value in the variable vk by the value in vk plus 1. That's the second step. And the last step, you take the temporary value that was originally the value in vk and assign it to vk plus 1. And those three steps are the three steps as you can see here. And here in this method, we only have to define this temporary value as an integer. The swap method takes as an argument the array and the index that you want to swap the variable based on. So this index is k. So since you know that this is k, the other variable is the next one, which is k plus 1. Now we assume that v is in register A0. So this is the base register of the array v, k in register A1, and k right now it's the index, and the temporary value is in one of the temporary registers. We used T0. And what we did here is first we need to prepare the array members. As you can see here inside the body of the procedure, we have vk and we have also vk plus 1. And if you remember, I mentioned that if you have an array, you have three instructions that you need to use: shift left logical, followed by add, and then at the end, now you can do the load or stop. So the shift left to multiply by 4. So you shift left the variable by 2 position to do the multiplication by 4, by the constant 4. And the add, you add the offset to the base register. And after that, you can use the load or stop. And this is what we did in the assembly code that you can see here. This is the swap method. And first, we shift left A1 by 2. A1 now is the index, which is k. Since we shifted to the left by 2, this means that we are multiplying by 4. After that, we get the result, and we add it to the base register to generate v of k. Now we know that v of k is in the temporary value 1, the address of v of k in the the register T1, we can now load v of k if we use the offset 0. If we add to the offset 4 more bytes, this means I'm getting the next index, which is k plus 1. So right now, I loaded the data that was in this location. That is, this location is pointed to by the address stored in the register T1, and you load the value into T0. Similarly, now for the VK plus 1, since we used 4 more bytes in the offset, so you load this into another temporary register. We used T2. Notice that we are using T1, so we jumped it, so we don't confuse ourselves. Now, you can do the swapping by using the store, but now the T0 is going to be stored in the other location. The T2 is stored in the previous location at 0. So now T2 will be stored into T1 at the offset 0 and T0 at the offset 4, meaning that we are doing the swap. After that, you jump return to the return address. Now, we study the swap because we know that the sort, which is our original example, the bubble sort, is going to use the swap. Because usually, if you have an array with certain members, let's say 5, 4, 1, 3, 7, let's say, if you are comparing those two at any point of time, then after the comparison is done, you needed to swap. Then at that time, you use this swap function to swap the 1 in place of 4 and 4 in the place of 1, and so on. And then you continue doing the sort. Now, to understand the source, the sort, this is the array bubble sort. It has 2 for loops. The first one, the index I start from 0 up to n, and you increment the index every time. So if, for example, you have an array with 5 members, meaning that n is 5, then you will start from 0 up to 4. This is why we have 0, 1, 2, 3, and 4. Now, the second for loop, this is, as you know, nested for loops. The j is equal to I minus 1. So whatever value of I, the j is going to be this I minus 1. So at the beginning, it would be 0 minus 1, which is going to be minus 1. So at the beginning, the I is going to be 0, and the j is going to be minus 1. What happened to the j is you compare it if it is larger than or equal to 0. If that's true, then you go and continue what's inside the for loop. And every time when you're done, you decrement the value of j. Now, the condition that, or the sort condition is when v of j, you compare v of j to v of j plus 1. If the data in v of j is larger than the data in v of j plus 1, then you do a swap. And to understand how is this going, I tabulated the operation for an array with 5 members. Let's say randomly the members are 8, 3, 5, 1, and 7. So at the beginning, I is equal to 0 and j is equal to -1. And if you apply this condition, -1 is not larger than or equal to 0. So you do nothing. And then you will get out of the for loop and you will start again here. When you start here, you will increment the I by 1. So the I will become 1. And notice what happens to the I. You start with 0 and then you stay at 1. After that, you increment to 2 and then 3. At the end, you'll end up with 4. Now, what happens to j, since I is equal to 1, j is going to be I minus 1, which is 1 minus 1 is going to be 0. So notice now that j, which is 0, is larger than or equal to 0. It's equal now. So this condition is satisfied. You will go down to the if statement. And in the if statement, you will compare the array v in terms of the index j. So you worry about j only. So j here is equal to 0. So you compare j of 0, or the array name is v. So this should be v instead of a, not to confuse you. So these are v's. What happens here, you compare the v of j, and j we know it's 0. So v of 0, which is 8, you compare it with v of 0 plus 1, which is v of 1. You compare it with the 3. If whatever in 0 is larger than 3, and it's satisfied here, then you have to do the swap, and the swap will swap the 8 and 3, as you can see here. And after that, you will decrement the j, and you will find that the j is -1. So you get out of the for loop. We are not going to repeat this every time because of the space in the slide. Now, we will increment the I to 2. And then the j is going to be 1 step less than the I. So if it is 2, it will be 1. You begin at 1. And then, since you are having the j at 1, then you will compare v of 1 with v of 2. And as you can see, this is larger than this, so you need to swap. After you finish the swap, we decrement the value of 1 to 0. And right now, you will compare this, the gray to the green, and you found that this one is not larger, so you don't do the swap. After this, you will decrement the j, it will be -1, and you will get out of the inner 4 to the outer 4. You will increment I to 3. Now it is 3, so j will be 2. So you compare 2 with the location 2 with the location 3, and 2 is larger than the location 3, so you need to do the swap. And after that, you will decrement the j, and you will compare those two. And since this is larger, you will do the swap, and then decrement the j. And again, you need to do the swap. So 1 between the 3 and 1, it becomes 1 and 3. After that, you will decrement the j. It will be -1, and you will get off the inner for loop to the outer for loop, where you increment the value of I. It would be 4, and you will start the j with 3 and go down to 1 and 0. And at this point here in this row, you will compare 3 with 4, and you notice that you need to swap. And after this, you'll compare those two, no need for swap. Those two, no need for swap. And the last two, also there is no need for swap. And as you can see, what happens here, this array is now for sure sorted from this sorting is ascending from the lesser number to the largest number, 8. If you want to do the descending order, instead of the larger than here, you will use less than. However, we will keep using the same in our assembly language that we will see in the next few slides. Now, we have the same sort that I just show you. It's here in the for loop. There are 2 nested for loops. The I start from 0, and you increment the I. The j from I minus 1, and you decrement the j. Now we have the 2 conditions together in the condition of the for loop. The j must be larger than or equal to 0, and vj must be larger than vj plus 1. It will work the same. Now we have the same assumptions. V is in a register, the V address. I mean, the address of the array V is in A1, and the number of, or the size of the array is in register A1. And the I, the index I and the index J are stored in S0 and S1. It's good to remember that since we are using this comparison and we have larger than and we have larger than and equal, we use for larger than set less than followed by branch equal. We use for larger than and equal, we use set less than and branch not equal. So it's good to remember those. We can refer to them when we build the assembly code. So in the assembly code, what you need to remember how the for work. The for works by first executing this statement and then checking the condition. And after that, if the condition is true, you go and execute what's inside the body of the for. Once you're done, you go back and do this statement. So if we want to number them, this is number 1, number 2, number 3 is the body, and number 4 is the last statement. Similarly for this one, this is number 1, and then number 2, number 3 would be the swap, and number 4 is the decrement. At this point, we will move to the procedure body. And as you can see, what we did here is we saved the argument, which is A0 and A1, into S2 and S3, respectively. And to remind you, this is the argument, which is the same as the argument of the swap, except that this is the full size of the array instead of a certain index. And this is the array V. So we know that the base register of the array is in A0, and we moved it to S2. And the size of the array is in S3. Notice that we use the pseudo instruction move, which is built using add immediate. Now we will do the first loop. We notice that the first instruction in the first loop, I is equal to 0. And this is what we did here. We moved 0 to S0 because S0 now is the I. After that, we will execute this one, this statement, which is if I is less than n. And we go here, we know that when we compare I, if it is less than n, we will use set less than followed by branch equal. And this is what we have here. Set less than followed by branch equal. Notice we need to keep the registered numbers, the lowest, which is 0 here, and the highest 3 to keep the same format, which is set less than followed by branch equal. Now we know set less than if there are less, if S0 is less than S3, meaning that I at T0, this T0, if this is true, it would be 1. It will be 0 if this is not satisfied, meaning that S0 is larger than or equal than S3. So what happens? If it is okay and it's true, this would be 1. And if you compare 1 with 0, they are different. So you won't branch to the exit. You will continue inside the loop. Otherwise, you will branch to the exit. So you will continue inside the body of the for loop. But before that, let's check what happens if you exit. So if you exit, you will exit to exit 1. You will try to look for it, and you won't find it in this procedure. It will be in the next slide, which is the exit of this for loop, meaning that you're done with this for loop and you are exiting right here. And after this, you return out of the sort method. That's exit 1. Now, when you're done with the branch equal, which is doing this instruction, you will do the for or this body right here. So don't forget that we need to do this after we finish the body. So we will come to this later. Now, in the body is another for loop, starting by assigning j to, or assigning I minus 1 to j. And this is what we did here. We assign j to I minus 1. We know that I is S0. We add immediate to minus 1, and we assign it to the destination would be in register S1, because this is representing the j. And then we have set less than with branch not equal, because we are trying to get this condition. And we use set less than followed by branch not equal. Set less than followed by branch not equal. And you can see that in similar way like before, we will exit if this is not satisfied. If this is not true, we will go to the label exit 2. Exit 2 should be the label that will send you back to the first for. This is the label for the first for loop. This is the label for the beginning of the second for loop. And you can notice that when you exit, you need to add immediate I to itself by 1, which what you're doing here is an increment. So you take I and then you add it by 1, and after that you jump to the first for. And this is what happens here, that if this is not true, you need to exit out of this for loop. What you need to do is you execute this one and then go back to the for, meaning that you check this condition again. And this is what happens here. We have the +1, the increment, and then you jump back to the first for loop. Now notice that we have 2 conditions here. This is the first condition, and this is the second condition. If this condition is not satisfied or false, you go out of the for loop. Or if this is not true, you get out of the for loop. So this is why if this condition is not satisfied, then you move to exit 2, which is this condition, as j is larger than or equal to 0. Also, when v of j is larger than vj plus 1, you go to the first for loop. And this what happens here. You will branch to the exit 2. But what we did here, since this comparison, it will take some or few number of instructions, because you need to prepare the v of j, and then you prepare the vj plus 1, and then you do the comparison by using the set less than followed by branch equal. And this is what we did here, following this line. So if this is true and you don't branch to exit 2, then you go to the body. First, you shift left logical by 2, because we need to multiply j by 4, and then add the T1 to the base address S2, which is the base address of the array V. And now we have it in T2. And right now here, we prepared V of j. And we can load it to another temporary value, T3. Now, luckily, the VJ came, our VJ plus 1 is just the following address, meaning that we need only to change the offset from 0 to 4. So you don't have to do shift to the left logical followed by add, because you already did it for the first one, which is V of j. For V of j plus 1, you just change the offset to be able to load it to the other temporary value. Now we can compare those two by set less than followed by a branch equal. And this is what we did here. Now, if you compare these and they don't satisfy the condition, which is this condition, then you exit out of the loop to the first for, which is this exit 2, as we stated before. Now, if you did not move to exit 2, meaning that the condition is satisfied, then you need to do the swap. You need to do the swap, which is this one. And to do the swap, you prepare the arguments for the swap procedure. So the first argument is S2, which is the base register of the array V, and you move it to the first argument, which is A0, and then you have J, which is in S1, you move it to A1, and now you can jump and link the swap function, meaning that here we are calling the swap. There's something here that you need to notice. Notice that the A0, what we did here was take S2, we took S2 and put it in A0. If you look in the all state instructions before, you won't find any of the instruction updating the value of S2. So basically, we could have taken this out and we kept A0 the same, because there is no change in S2. This is why we say that it's the same old A0. But for S1, there was a change. We changed the S1 when we decrement the J. I mean, when we assign the J to I minus 1. So we are changing the S1. Not only here, also in the after you finish the swap and come back, you will come back here, meaning that you will, after you finish the swap, you will come back to here and you need to decrement the J. And this is what happens. You decrement the J by using add immediate, register S1 with -1. So you decrement the J. So notice again, S1 is changing. And then after that, you're done. So you jump to the first or the inner for loop, which is this. and redo it for the next J and so on. Notice that this one will jump here, and this one will jump over here. Now, similarly, we have exit 2. You can go to exit 2 because the first condition is not satisfied, or because the second condition is not satisfied. You will also go to exit 2. Now, where is exit 1? Exit 1 is actually in the next slide right here. And you notice that in this slide, it tells you that this is the beginning of the sort. If you notice here, there was no label for the sort. You have no idea where is the beginning. We used it here because we didn't have space to list all of these. So this is the sort function. And you will notice in the procedure that we used a lot of saved variable. We used S2, we used S3, we used S1. And also we need to save some other important values for the procedure, because every time you call the swap and then you come back. So what happens? We saved S0, S1, S2, and S3, and also the return address, because they are modified. The S0 is modified, S1 is modified, 2 is modified, 3 is modified, and also you are calling another function here, which is the swap, and you need the return address to be saved. And this is why we save those variables in the stack. Since we have 5 variables, we need 5 times 4, which is equal to 20. So we add immediate to the stack pointers minus 20, meaning that we are dropping the stack pointers to make space for 5 variables, and then we save every one of them. Notice now the offset. Since you are using 20, the first one would be in 16, followed by 12, followed by 8, followed by 4, and then you end up with 0. Notice that what we did beginning from the 20, every time we are subtracting 4 until we get to 0. So we saved all these variables, and then we start doing the procedure, which is this procedure. Once you're done with the procedure, meaning the last statement was here, and you needed to exit to label exit 1, you will come here. You will come here, and at this point, you need to pop everything from the stack. We will do it in the opposite way. As you can see here, instead of the store, you will use the load, and you are actually copying the rest. And the last one is add immediate to do the real pop, and at the end, you return to the main function probably, or any other function that called the sort procedure. So this complete example showed you different aspects that we already discussed in the previous video. Now we will move to some of the effects of compiler optimization. So let's assume that you compile the code, this code, the sort code, with the GCC compiler for the processor that is Pentium 4. That's one of the old processors from Intel, under the operating system Linux. So what we did is we're trying to calculate the performance, and we know that the performance is related to, let me write it down, that the performance is 1 over the execution time. And we know that the execution time is the instruction count times the CPI times the CCT, or the clock cycles. And this is why we have the instruction count, the clock cycles, and the CPI, because these are the 3 members of the execution time, and after we take the reciprocal, we get the performance. So what happens in the x-axis, we use this GCC without any optimization whatsoever. And then we used the compiler with a certain optimization called 0.1, and then another version of optimization called 0.2, and then a third optimization 0.3. Those optimizations are different than each other. So what happens is we're trying to calculate the performance. So first we get the instruction count, and we notice that if there is no optimization, the instruction count sky high. But with optimization, the instruction count is reduced, which is a good point. And based on the optimization, we found out that 1 is giving you better instruction count than 2 and 3. And you can see first 1 is better than 2, and 2 is better than 3. Now, in terms of clock cycle, if you don't do any optimization, you need a lot of clock cycles for the time for the clock cycle. It would be huge. For optimization 1 and 2 and 3, they are very close to each other if they are not the same. So if you do the optimization, there will be huge reduction in the clock cycles, but the version of optimization doesn't make big difference. Now, in terms of the cycles per instruction, how many cycles you are spending for each instruction, since you don't do any optimization, you don't have to have more clock cycles for every instruction. Now, every optimization you do means that you need more clock cycles for every instruction on average. Optimization 1, you have a little bit more, 2 a little lower, and 3 is the lowest. Now, we calculated the performance for each one of them. We found that if you don't use any optimizers, the performance is really bad. And you shouldn't do that. You should find an optimization and adopt it. And as you can see, if you were to choose between optimizer 1 or 2 or 3, you should get the one with the highest performance. And to my eyes, this is the highest performance, and you should get the third optimizer. Now, notice that this is true only for compiling the code with GCC. Now, if you compiled another code with GCC, you might find other results. Maybe at that time, 1 is better than 3. So it depends on the code that you are running. Now, also there is an effect of the language and the algorithm. Here we get the performance for the bubble sort, our sort, the one that we discussed. There is another type of sort called the quick sort, and we did the same. We didn't show you the code, but we did get the calculations in terms of performance, and then we try to get the speed up comparison between the two. So in the x-axis, we used C language one time with no optimization, and we have the 3 optimizations, 1, 2, and 3. And we also used the Java using the interpreter, the simple interpreter, and this is terrible. And then the next version is using the Java with the just-in-time compiler, which is way better. So what happens in the bubble sort, you can see that the highest performance is the using the C language with the third type of optimization. If we used another language that do the same thing, we used Java, and we found that the performance is a little bit low. If you didn't use the just-in-time, the performance is the worst among them. So this is telling you an information. If you are using Java, make sure that you are always using the just-in-time. Now, for the quick sort, we changed the program now, and we found that the difference is very clear. Now, the third optimizer of the C language has a clear victory in terms of performance. Now we get the speed up. When we get the speed ups, we are comparing this number to this number for each case. So you can see here that we divided, let's say this is 1.9, and this is like 2.4. So when we divide those numbers, we get this value right here to get the speed. And we notice that in terms of speed up, the hugest or the best speed up that we gained is when we are having no optimization whatsoever, because you can see it's clearly a big jump when you are comparing those two sorts, because this doesn't have any optimization. So this is like a misleading information. And the speed up here is the best since you calculated the performance and you found that this one is the best. Now, the lesson learned so far that the instruction count and CPI are not good performance indicator in isolation. You need to have them, they are very critical, but you need to take care of other things as well. Like the compiler optimizations, they are very sensitive to the algorithm. When you are using Java, make sure that you're using the just-in-time. And here is a conclusion. There is nothing that can fix a dumb algorithm. If you do a really good hardware and a lot of optimization, and you made sure that you use a really good language, but your algorithm is dumb, then you will have a really bad performance. And we discussed this at the beginning. We see that there is so many aspects that affects the computer architecture, and one of them was the software or the algorithms. Now we will discuss the array versus pointers from the assembly language point of view. The array indexing involves multiplying an index by element size and adding to array base registers, meaning you will have the index I, and every time you have this index representing the offset or the displacement, and you need to add it to the base register every time. And this is what we have with the three instructions that I usually try to remind you of: shift left logical, followed by add, and then at the end you can do the access to the memory. Load is an example, or store. Now, using a pointer, that's another way. The pointers correspond directly to the memory address, which can avoid the indexing completely, and this will give you huge advantage. To see this, here is the there are two methods. They are simply clearing an array. If you have an array with a certain size, you go through the array members, and every time you assign the value 0 to this array member. If you do it with index, you should do it this way. This is in C. This is also, I believe, in Java as well. And using the pointers, instead of having this symbol, you will have the star. This means that this is the pointer to the beginning of the array. And you define a pointer P, and you will, instead of using an index, you will move through the array member using the pointer. So at the beginning, the pointer will be equal to the address of the first member of the array. And then you will compare if the pointer is less than the address of the last member, meaning that you went to the last location. As long as you are lower than that, you keep going through the loop. If you reach to the last member, then you stop. When you see this add, sample, you can say instead of at, you should say the address of. So this pointer is equal to the address of array of 0. Now you check if the pointer is less than the address of the array of the last member, which is residing at the index size. What you do, you increment the pointer, and the location where the pointer is pointing to is going to be 0. So you clear this way. So what happens if you write the assembly language for this one? This is a good exercise for you to write down here. I will quickly go through it. First, you move 0 to T0 because you need to clear the index I. After that, you check if the I is less than the size. And to do this comparison, you need to check if you have set less than followed by branch not equal, since this is what you have. And if this is true, you will continue through the loop. If it is wrong, you will exit out of the loop. Now, you notice that in the branch equal, you will move to the loop, which is loop 1. If this is not true, you will execute the instruction right after that. And this means that you are getting out of the loop. Now, what happens here, you prepare the array of I by doing the shift left logical. You multiply the index I by 4, followed by add to add the index I to the array base register, which is A0. And then you have T2 already calculating the index or the offset added to the base registers. And now you what you do is at this location, you assign 0 to it, meaning that you need to store 0 to that. Once you're done with this, you increment the value of I, and then you check the condition. So we did some optimization here where we assign the I, and then we right away calculate this one, because we know that the first member, which is I equal to 0, we surely have to clear it, and then we go and increase the value of I here, and then we could check the condition and so on. So instead of calculating like this, 1 followed by 2, and then 3 and 4, which is the normal way, we did it this way, 1, and then this is 2, and then after that, we did 3, and then we check 4 and go back again to 2, 3, 4, and so on. And this is what we have. Notice that when the branch is satisfied, you go to the first of the loop. So you need to execute all these instructions through the loop. 1, 2, 3, 4, 5, 6 instructions. Now, if you use pointers, you no longer have to deal with the index I. So you don't shift left and work with the I. What you are working with now is the pointer that points to the array, which is called array. So now this array base register is A0. What you are shifting now, you are shifting the A1, which is the argument that you see here. So this is A0, and you have A1 here. So what you are shifting here, you are shifting the size of the array to the left by 2. And then you add this one here to generate the array of the size. We are doing this because we need this entity. So we shift left and then you add, and then you can get this value. What happens here is you are assigning to this value the value of 0, as you can see here. So now you know in that memory you will have the value equals to 0. And after this, you add immediate. Notice now, before we added, when you increment the I, you increment by 1, because you know when you go back to the first of the loop, you will shift it by 2 to multiply it by 4. But here we don't have to. We can directly have the value T0, which is this one, and we add 4 to it to go to the next member. So we are adding 4 to the pointer that we have, which is T0. So T0 now have the pointer value. And this is why we are able to, in the beginning, to do this. We assign 0 to whatever pointer at T0. We're assigning 0 to it directly. And after that, we add 4 to go to the next place. So we add to T0, our pointer, we added 4 to it. And after that, you check your condition, which is this one. Set less than followed by the branch not equal. If this is true, you will go through the loop. If not, then you will be outside right here. So this is actually calculated right here. And then you will go through the loop this way, and you can see that you are only having 4 instructions, while here we have 6 instructions. So if we, for example, say that the size have 100 members. So in these 100 members that you will clear, you need to go in through the loop for 4 instructions for every one of this 100 members. But here you go through 6 instructions. So this will be a better optimization. If you want to check this one against this one, you see that there is a move here, set shift left logical, followed by add, followed by the store, followed by the add immediate, set less than, and branch equal. So the same instructions here and here, but the loop is different. You are having 6 instructions, here you have only 4. So let's look at this again. The first one is having this statement. We did it here. And then after this statement, we did the same. Directly, we went here. And this is what we did here. We did shift left followed by the add. And then we did the store. So we store here, right here. We did the store. And we have those two outside the loop, because this one that we will compare against it's not going to change every time we compare. So we can do the shift left and add outside the loop. And this is what we did. We multiplied the size by 4 to prepare T1. And then we have the array of size, because we added the T1 to the base register A0, and now it's ready in T2. So when we want to compare, this T2 is ready. We don't have to do it inside the loop. And inside the loop here, what we did is we did the store here, which is this store. We did it here. And then we did the add immediate, meaning the pointer, we incremented by 1. And we incremented the pointer this way. Since it is a pointer, we add 4 to it to go to the next position. And then after that, we did the set less than and branch equal to do this comparison and so on. So you can see the big advantage of the pointer. Now the comparison of the array versus pointer, you multiply strength reduced to shift. Array version require the shift to be inside the loop, but part of the index calculation for this incremented I, and this is why it takes many instructions inside the loop if you use the array version. And this is contrary to incrementing the pointer. There are certain instructions that you can do outside the loop. The compiler can achieve some same effect as manual use of pointers, induction variable elimination, and this is better to make program clearer and safer. But this is actually, if you are going to study a course related to compiler, you will face this at that course. And now we will see some real stuff. We will start with the ARM instruction, or the ARM ISA. So there are similarities, many similarities actually between the ARM and the MIPS. Now we know the MIPS and we study. The ARM is the ISA for the Apple processor. So they are announced the same year. They use instruction size 32-bit. The address space is 32-bit. The data alignment, they are aligned. Now the addressing mode in the MIPS, we have only 3. In the ARM, we have many addressing modes. We have up to 9. The registers, they are in MIPS, we have 32 registers. Each one of them is 32-bit. But here we say they are 31 because we know that one of them is constant, which is the register 0. So we took it out. And for the ARM, there are 15 registers, half the number of the registers. The input and the output, both of them are memory mapped, and we will touch this later. Now, the compare and the branch in the ARM, they used condition codes for the results of an arithmetic or logical instruction. You have negative, you have 0, you have carry, and you have overflow. So for each instruction, there is a status for it. If that instruction caused an overflow, there is a flag for it. If that is true, this flag would be 1. Similarly, if an instruction, let's say it's an add, and the add generated a carry, that status will be 1. So you compare instruction to set condition codes without keeping the result. Each instruction can be conditional. The top 4 bits of the instruction word have the condition value, and you can avoid the branches over single instructions this way. And you can see there is so many details in the ARM that we didn't talk about when we have the discussion in MIPS. Anyway, it's good to know that these are the instructions for the ARM. We compare the ARM with the MIPS for the R type, for the I type, and for the branch and the jump. You can see that all the instructions are 32-bit. You see the similarity between the MIPS. Remember, we have 6, 5, 5, 5, 5, and 6. Here we have 4, 8, 4, 4, 8, and 4. This is their breakdown of the R-type instructions. In the data transfer, remember we have a constant with 16 bits. They have only 12. And they are having more opcode bits, meaning that you can add a lot of different instruction in the ARM ISA. Now, in the MIPS, you have the branch, which is an I type. So you have the constant with 16 bits. In the ARM, you have up to 24, which means that you can branch far away already in the ARM. By the way, I think here you need to be careful. We are talking about the opcode here, which is only 6 bits. I mean 6 bits in the MIPS, and in the ARM they are 4 bits, which means that the number of instructions here are lower. So to know exactly if they are lower or higher, you need to study the ARM ISA in detail. What the OP-X means, what OP means, what is the first RS1 and the RD, and so on. Now, for the jump, remember the jump, we have 26 bits here. Here we have only 24 with two opcodes, OP-X and OP. So there is similarity. Now we will move to the x86 instruction, and that's for the Intel processors. It has evolution, so this is a little bit history. So it started with 8080, and then 8086, and then 8087, and then 8286, 8386, and so on. And you see the dates. At the beginning, it's 88-bit processor, 16-bit processor, and then you added the float point co-processor in 1980, and then the 24-bit addresses with the MMU and the 32-bit extension. And you can read the details for that. And further evolution, we reached to Pentium 4 at 2001, and there was every few years, you are adding more features to the x86 ISA. They introduced the pipeline and the on-chip cache and the floating point in 89. In 93, the Super Scalar, 64-bit data path. And that was a huge jump because the Super Scalar can execute 2 instructions or maybe more at the same time. And then at 95 and 97, they have a new microarchitecture, and they called it Pentium 2, and then they have another version, Pentium 3, and then 4. And further, they advance it every time. And they have, for example, 2003, they extended the architecture to 64-bit. In 2006, they added virtual machine support. And then they worked with the AMD 64, which was announced in 2007. And then Intel declined to follow, and there was certain problems here. And then they do the advanced vector extension, which was announced in 2007, 2008. If Intel didn't extend with compatibility, its competitor would do that, and they would win. So they need to work with the compatibility, and the reason, as you'll see it in the next few slides, but here there is a good note that the technical elegance doesn't necessarily equal market success. And Intel had to work with this for a long time. Now, the basic x86 architecture, the basic x86 registers, as you can see, they have those registers that are not the same level. Sometimes they are 32-bit, sometimes they are 16 bits. And that caused troubles later when you build the architecture, because you have kind of 2 types of registers now. And also the next one, we have the addressing mode. We have 2 operands per instructions. Remember, in the MIPS, we have 3 operands, 2 source and 1 destination. In the x86, in the x86, you have only 2 operands. And you have many, or you have the following address modes. Either you do the address in the registers, or you have the address as a base with displacement, and we know those 2. Or you have the address with something complicated, as you can see. The base plus 2 to the power of a scale times the R index. And this scales could be 0, 1, 2, or 3. Or you have the same thing, but also with the displacement. So you can see that there is some complexity for the addressing mode in x86. This what causes this terrible problem for the x86. In my opinion, that's causing a lot of trouble in the architecture, because now there are certain instructions that is 4, 4, and 8, which is 16 bits. Some other instructions 32 plus 8. It's not even a power of 2. Another instruction have different length, and so on. So you have instructions with variable lengths, and this causes difficulties when you work with them. Now, this is usually called for the x86 called a CISC, which is a complex instruction set computer. It's a CISC system. While the MIPS and also the ARM, they are called RISC, which is a reduced instruction set computer. I suggest you read about those so to see the differences. And you can see x86 making things complex. Different registers, they are not aligned. Also, the instructions have different lengths, while in the MIPS, they are organized. So the complexity is reduced, while here it's very complex. So the Intel x86, and then they have another name, which is the IA32. It has a complex instruction set, which makes the implementation difficult. You have hardware translate instruction to simpler micro operations. You have simple instruction 1-to-1, and the complex instruction 1-to-many. And this is what happened for Intel. This is what happened for the MIPS and the ARM. It's micro engine similar to RISC. The market share makes this economically viable. It's comparable performance to the RISC. The compiler avoid the complex instruction. So basically, what the x86 did when they moved to the IA32, they tried to move away from the CISC and somehow get to something similar to RISC. Now, this is the ARM version 8, which is the 64 bits. And at the time when your textbook was published, this was the state of the art. So the ARM V8 instruction, you move to 64 bits, and you can see that the ARM V8 resembles MIPS in many ways. The changes from the old version V7, there are many things that changed. Some of them you might be aware of. Some of them maybe you need more knowledge to understand what do they mean. So there was no conditional execution field. The immediate field is only 12-bit constant. They dropped the load and store multiple. That was an instruction, they take it out. The program counter is no longer a GPR, general purpose register. The GPR set expanded to 32. Remember, they were 15, so now they have more. Addressing mode works for all word sizes. There was a limitation before, and in version 8, they removed this restriction. They introduced the defined instruction, which is something nice. The branch of equal and the branch if not equal instruction, they were introduced in ARM V8. So basically, at the beginning, they didn't believe in MIPS. And when the V8 comes, they say, oh, let's do like MIPS. At this point, we will move to the fallacies and pitfalls. One of the fallacies, you think that if you have a powerful instruction, an instruction that could do addition and subtraction and probably something else at the same time, or a very long instruction where you can add many variables, let's say 10 variables, and you get the result in a destination. So you have you have add A, B, C, and then you put the result in Z, let's say. So that's a complex instruction. You might think this is a powerful instruction. And you might even think that powerful instruction would lead to higher performance. No, that's not the case. Fewer instructions are actually required if you do that, but complex instructions are hard to implement. You think by doing the powerful instruction, you will get a higher performance because you will have fewer instructions, since you are combining the little instruction into really big ones. But what happens, they become complex instructions and they are hard to implement in hardware. And this also in turn may slow down all the other instructions, including the one that you believe that they were simple. So the compilers are good at making fast code from simple instruction. You should keep this in your mind. So that is not true. That's a fallacy. Also, you think that if you code yourself as a user using assembly code, this will cause a high performance machine code. It's not the case. Usually the compiler do a lot of things that you don't have to deal with. And the compilers do it much better than a user, a human being, writing the assembly code directly. So modern compilers are better at dealing with modern processor. More line of codes equals to more errors and less productivity. And this is what humans tend to do if they code. So one might ask, well, then why we are studying the assembly code if the compiler is going to do it for us? What we did here is for your education purpose. That's the first thing. The second thing, most of the time you need to understand an assembly code if you look at it. Especially if you are working, let's say you are a cyber security major, and there was an attack or somebody who added some lines to generate a Trojan horse, or a virus was embedded somehow. So if he did that at the assembly language level or at the machine code level, if you have good knowledge about assembly code, you can catch that and deal with it. So it's good to have assembly language knowledge. Now, here are some fallacies. You think that backward compatibility means that the instruction set doesn't change. So let's see in x86. Since 1978 up to 2012, if we looked at the number of different instructions, meaning like we have add and add immediate, sub and sub immediate, and things like this, and you keep counting them, in 78, they were a little bit shy of 100. In 2012, the jump is up to a little bit shy of 900. So from 100 to 900. Even though x86 was caring about the compatibility, the backward compatibility, meaning if an instruction that was working in 78, in 80, it will still work, and in all of the other years. But that doesn't mean that the instruction set doesn't change. What happens is they do change by accreting more instruction. So you have more instructions throughout the years. Now, here are some pitfalls. The important one is this one. Remember, sequential words are not at sequential addresses. We are jumping by 4. We are incrementing by 4. And this is why we use shift left logical. And then you have 2 in the instruction, because you want to multiply by 4, not by 1. Also, this is related to the pointer, and we saw the advantage of pointer. Keeping a pointer to an automatic variable after procedure return is a pitfall. Be careful of this. For example, passing a pointer back via an argument. What happens? The pointers become invalid when the stack is popped. Remember, when you have a procedure, what we do is popping at the end. If the pointer was popped too, then you can't use it anymore. It becomes invalid. So make sure that you don't use the pointers inside the a lot of procedures without being careful. Now, as concluding remark, we have 4 design principles throughout the whole videos. First, simplicity favor regularity, and this is what MIBs and ARMS did. Smaller is faster. Make the common case fast, and good design demands good compromises. If you keep those 4 points in mind when you design a new ISA, this will gain a lot of advantage in terms of performance when you try to implement the hardware. You have layer of software between layers of software and hardware, like the compiler, the assembler, the hardware. The important thing that we studied in this chapter, that the ISA is the layer between the software and the hardware. MIBS is a typical RISC ISA, reduced instruction set computer ISA, contrary to x86. Basically, and this is my own opinion, ARM processor or Apple, their ISA is better than Intel, which is the x86. And even the Intel, they are trying to move away from CISC and getting to RISC. Now, we discussed many instructions. We talked about the add, the subtract, the add immediate, the load, store, the load word, store word, load byte unsigned, load half byte unsigned, store byte, load upper immediate, and or nor and immediate or immediate, shift left logical, shift right logical, branch equal, branch not equal, set less than immediate, set less than immediate unsigned, jump return, and jump and link. We study all of them, and we see them through many of the assembly codes. Also, these are the breakdown of those instructions. Those are arithmetic, those are transfer rates, data transfer. This one is logical, this one is conditional branch, and this one is jumping, and this is their frequency in SPEC 2006 of the integer type. So the SPEC for the integer, this is the breakdown. For the floating point, this is the breakdown. Notice that in the floating point, we have 0 jump. Actually, the jump is very low because we jump only a few times. But as a big difference here is this part. In the logical operation, in the integer, we have more than the floating point, because in the floating point, we care about the arithmetic a lot more than anything. So we have many arithmetics in the floating point compared to the only integer. And we said that we will discuss those 3 tables. And I believe at this point, try and read all of them. And you will find out that we touched them somehow inside the video. And this is the opcode table for your reference at the end of this chapter.